Hello. Today is March 2nd, 2021, time in Dallas, Texas in the USA, and it's March 3rd in India time. And I'm Bhavani Thuraisingam from the University of Texas at Dallas, and I'm giving this keynote address at the International Conference on Mathematics and Computing. And I'm very honored to give this presentation, and thanks for inviting me. And I'm recording this presentation because just in case there's a technology glitch when I actually give this presentation probably around 9.5 hours from now. So in case there's a technology glitch, the organizers can play this recording, okay? So, and again, I'm Bhavani Thuraisingam from the University of Texas at Dallas. I work in cybersecurity and data science. So I'm going to share my screen. So just a second, I hope my screen is being shared. And also I hope it's being recorded. Yes. Okay, so I just want to make sure that all the, right, so it is being recorded. And I don't know why this is, okay, so I just want to move this down. Okay, so my talk is going to be on integrating cybersecurity and artificial intelligence, data science with applications in Internet of Transportation and infrastructures. Okay, so 3 parts. Part 1 is integrating cybersecurity and AI data science. And here I will discuss big data security and privacy, privacy-aware quantified self, data science, machine learning for cybersecurity applications, and securing data science, machine learning, AI, right? So one is sort of some of the challenges with big data and what happens when there is privacy and how do you apply machine learning, say, for intrusion detection and malware analysis, and what happens if the machine learning techniques are attacked. Second part is security and privacy for Internet of Transportation and infrastructures. And the third part is applying part 1 to part 2. So how do you apply security and AI for Internet of Transportation and infrastructures? This work has been funded by a number of our sponsors, and I would like to thank our colleagues, Professor Alvaro Cardenas, Murad Kantajulu, Latifa Khan, and our former PhD student. He is now Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. So part 1, integrating cybersecurity and AI/machine learning/data science. So I'm bundling all 3 topics together, okay? So first, I want to give a bit of a motivation, data mining, security, and privacy. So I introduced the idea of the privacy violations that could occur through data mining almost 25 years ago at the IFIP conference in 1996 in Como, Italy. It was a keynote address, and then another keynote address at the Pacific Asia Knowledge Discovery Conference in 1998, and then published, I call it a landmark paper because I was a program director at National Science Foundation. And so when you are a program director and you publish a paper in CKDD directions, so a lot of people are going to follow. So that paper had quite a few citations. And in a way that spawned a new area of research. So what's the idea? It's privacy preserving data mining, meaning that you have the original data and then you add some noise and then so perturb the data or randomize the data. And now you have a modified data mining process, and then you have the final modified result, but the end result should be the same. So when I joined the University of Texas at Dallas, in fall 1984, fall 2004, October 2004, we had a research student, Dr. Kantajalu and I, we had a research student, Li Liu, and she focused on privacy preserving decision trees and the perturbation method, and that was between 2005 and 2008. So there was a lot of work before that. IBM Almaden Research Center, and the researchers were focusing on privacy preserving association rule mining, and our work was on privacy preserving decision trees. And then in September 2014, there was all these discussions about big data. And so big data exacerbates the problem of privacy. And so we hosted an NSF workshop on big data security and privacy in September 2014. And we presented the results to the interagency working group in February 2015. Okay. And so what are the challenges? Big data, security, and privacy. So there are many technological advances, novel applications. It is possible to capture, process, analyze large amounts of data. And this data can also be used for security tasks. So these tasks from security point of view, authentication, access control, anomaly detection, user monitoring, and insider threat, and so on. You've got to understand that you can apply it for any applications like healthcare, finance, and so on. But our focus has been on security. And integrating the data collected on the web, we can identify connections and relationships among individuals. And that could in turn help with homeland protection, disease of outbreaks, and so on. And the collected data, even if we anonymize it, we can remove the identifiers when linked with other data, and it could re-identify the individuals. Security tasks, okay, such as authentication and access control, and that could require detailed information, right? Say for multi-factor authentication. And the information, if misused or stolen, can lead to privacy breaches. And so lots of directions, and that's what we are going to talk about. First of all, access control models for big data. So that's something I'm not going to discuss in this presentation, but I'm going to focus on privacy and big data for cybersecurity, and also what about secure machine learning. So these were some of the topics we discussed at the workshop. So one project that we've started is something called privacy aware quantified self. So you've got mobile users like smart devices, smartphones, and so on, right? So lots of information being collected. Right? There's photos and videos and texts and everything on our smartphone. And there is the recent emergence, sociologists and psychologists have been working on quantified self movement, where you collect lots of data from wearable devices and smartphones and analyze the data for personal life habits and give information to the users to help them to live better lives. Wouldn't it help if I open the refrigerator and start eating chocolates and ice cream, if my smartphone tells me, no, you're not supposed to do that. It's not good for you to eat chocolates and ice cream. But imagine the privacy implications, because a lot of data collected and shared often being carried out without the user's knowledge, bringing grave danger that personal data may be used for improper purposes. For example, data collected by a device monitoring blood glucose levels that can be used. And if you have diabetes, not only just you, your relatives, your blood relatives could also be denied health coverage. So privacy violations could easily get out of control if data collectors could aggregate financial and health data, right? And to tweets and Facebook activity and so on. Imagine, so much personal information could be violated. The lawsuits could be brought. So to address these growing challenges, we need tools. So yes, we need quantified self applications, but we want a privacy aware application. So we published a paper recently, about 3 years ago in ACM SecMat. So privacy aware policy based quantified self. So your data is being collected, data storage, data analytics, data sharing in our smartphone. And what data? Health, fitness, location, social media, image, video, and other sources. Some of the data encrypted in cloud storage, and some of the data anonymized, encrypted, shared data, query results through cloud services. It can go through to the cloud. And so this is our privacy-aware, policy-based quantified self-manager. What we are saying is that policies are guiding the entire data lifecycle. As more data is being collected, the storage on the device will not be sufficient to store all of the data. So we envision an encrypted cloud storage component where all the data and all less frequent data accessed are pushed to the cloud. Based on the access control policies, local applications running on the device will be given access to some of the collected data. When needed, these apps will be allowed to access some of the encrypted data. So this is our quantified self. There's mobile apps, data access framework for sharing and so on, collecting, and the data store and the cloud encrypted data store. So we may not want to store all of the data, right? For a 20-year-old, we don't need the average we don't need the daily weight, right? If you can weigh yourself like once a month, maybe once in 2 months, that's fine. So in some other cases, we may have to also delete data to preserve privacy. And once you say you delete data, is the data actually being deleted? And then we envision data sharing and analytics will be carried out using services running on the cloud. And based on different scenarios of the data could be sent without any modifications, heart rate data for medical diagnosis, some will be sent after sanitization, randomized response-based techniques to hide users' true response, and some will be sent in encrypted format. So again, what I want to stress is policies guide our data collection, data sharing, data storage, data analytics. Everything is guided by policies, okay? Okay, the second topic, data science for cybersecurity applications. So what are we going to do here? Big data stream classification. So we are using past models to bring classification models, predict the labels of future instances, and we want to help the decision making. So we've got big data streams, lots and lots of data, massive amounts of data continuously arriving, like network data, telecommunications data, sensor data, streaming data, continuous flow of data. It's very common in a connected digital world, and massive amounts. So say for network traffic is coming in, and remember in the old days, we only had one model, right? But now we have the capability to keep on updating the models. So we develop an ensemble of models, and remember the concepts are changing, right? As new data comes in. So we are continuously updating the models, and the old models get thrown away and the new models are replacing. And then if we test them, and then, we train them and then we test. And if it's attack, we block and quarantine. And then benign traffic stored in a server. And of course, expert will be, also consulted to model, to update all the models. Remember, ensemble of models. So we had a number of publications, and we applied it for a number of applications, in particular, insider threat. What is insider threat? Insider threat detection requires identification of rare anomalies where evolving behaviors tend to mask anomalies. So we have designed and developed ensemble of models for stream based on supervised learning and non-supervised learning, both, okay? So for supervised learning, the result is a classifier exhibits substantially increased classification accuracy for real insider threat streams. Relative to traditional supervised learning, we did support vector machine and one class support vector machine. We have also designed and developed unsupervised ensemble-based models, maintaining a compressed dictionary of repetitive sequences found throughout dynamic data streams of unbounded length. In unsupervised learning, we use compression because there's so much of data used to model common behavior. This results in a classifier exhibiting a substantial increase in classification accuracy. The ensemble of classifiers allows the unsupervised approach to outperform traditional static learning-based approaches and boost the effectiveness over supervised learning approaches. Okay, so here is the architecture. So we have all the system calls that we are capturing, the I chunks, right? That's the test training data. So we gather the I chunks and then extract features and then learn algorithms. So unsupervised Pbed, graph-based anomaly detection, and supervised support vector machine, we develop an ensemble of models based on the ensemble analytics. And so the I plus 1th chunk comes in, the testing, extract features, and then we run it through, and then is it anomaly or not? Okay, so that's what the algorithms we designed and developed, and we published quite a few papers on this. So again, we are applying, so your ensemble of models, several models are developed and the old models are thrown away. Okay, so that's the insider threat. Okay, data, big data, data science for cybersecurity. Now, then other topic is what happens if our data science techniques are attacked. Okay, that's a big problem, right? That's called adversarial machine learning. So adversary modifies the data to defeat the algorithms. We have to understand the adversarial learning. It's not concept drift. It's not online learning. Adversary is watching. This is a bad instance. Adversary is watching. This is a support vector machine boundary. These are the good instances, and that's how it's supposed to be. So adversary is looking at our data and looking at our algorithms. It's trying to thwart us so that, look, the bad instances are now showing as good instances, and we don't want that to happen, right? So in the end, there's a game that is being played between the data miner and the adversary. We are trying to mine and trying to make good use, do machine learning, adversaries trying to learn our behavior. So guess what happens, right? Okay, before I talk to you, we looked at a number of attacks, two classes of attacks, free range attacks and targeted attacks. So free range attacks, adversary can move the malicious data anywhere in this domain. And targeted attacks, adversary can move malicious data closer to the target point. So I won't go into all this mathematics. It's in our paper, knowledge discovery and knowledge discovery in data. It's the ACM, famous ACM conference. And so see what we do. So we are now learning, right, about the adversary. Adversary is learning. We are trying to thwart the adversary. The threat model, so test time deployment, attack modifies X to X prime, modify packet length by adding dummy bytes, add good word to spam email, add noise to an image. All these things are being done. So here is the adversarial support vector machine. The red instances are bad, and the crosses and the green circles are good. But what we are trying to do, black dashed line is a standard support vector machine classification boundary. We are studying what the adversary is up to and moving the boundary here so that more of the bad instances could be caught. Because remember, adversary is trying to push these to the good instances, right? So that's what we are doing. So we are trying to, according to some mathematical calculations, we are trying to move this boundary line here so that more bad instances are being caught. Okay, so the blue line is adversarial support vector machine. Okay, so that's the boundary line. Now you can ask the question, we can move this line right here so all the bad instances will be caught. But remember what happens if we move the line right here, even the good instances now are going to show as bad instances. And we do not want that. We don't want false positives and we don't want false negatives. Okay, so that finishes our part 1. Okay, now we go to part 2, security and privacy for Internet of Transportation and critical infrastructures. Okay, so Internet of Things, we know that, and it's being applied to Internet of Transportation. Internet of Things is our refrigerator connected to the television, connected to almost everything, our computers, our Wi-Fi's, our clocks, and so on, our smartphones. Internet of Transportation, similarly, all the transportation stuff, the trains and the trucks and the cars, between the cars and across cars and trains, and the roadworks, all are connected. And that's what we have these days. And so Internet of Transportation, IoT, Internet of Things, has major implications in the transportation industry. Autonomous vehicles aim at improving day-to-day activities such as delivering packages, improving traffic, and the transportation of goods. In the US, trucks alone carry an estimated 63.3% of freight of goods. AVs are not limited to ground vehicles, but also aerial and sea vehicles. And it's interesting, levels of automations for automated vehicles range, autonomous vehicles, from 0 to 5. And it's interesting that in the market, the ground vehicles like cars are poorly automated, level 2, and aerial vehicles like planes and even drones come under that, but planes are automated at level 4. Companies are investing heavily. GM spent 728 million in 2018, and 2019, I need to get those numbers because we are in 2021 now, 1 billion. We need to get the 2019 and 2020 numbers. While there's great potential in AVs and the improvements it can do due to the transportation industry, security and privacy concerns pose new challenges that need to be addressed as we move forward. Okay, so what did we do? Okay, first of all, AVs evaluate their environment using a variety of sensors, camera, GPS, global positioning system, inertial measurements, unit IMU, LIDAR, radar, ultrasonic sensors. Previous research has shown sensors are susceptible to malicious tampering, IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. Vehicles should verify the veracity of sensor signals before acting upon them. AVs rely on sensors to evaluate and interact with their environment. Sensors are susceptible to GPS spoofing. So here is the, okay, so at this level, sensor-based AVs rely on sensors to evaluate and interact with their environment. Inherited issues, sensors are susceptible to GPS spoofing and transduction attacks that manipulate environment physical signals like visual, sound, magnetic, and so on. And needed defenses, we need but classical computer security such as memory protection, cryptography, and authentication may not work against such AV attacks. So, and also no verification because of real-time constraints, AVs trust and act upon sensor input without any form of verification. So these are some of the challenges we are faced with. So what did we do? We developed a Pbed, physics-based anomaly detector, to build a reference monitor. That's the security critical component, using a physics-based anomaly detection algorithm for ground and aerial vehicles. The algorithm will consist of 3 parts: building a model offline of the AV's physical invariants, implementing an online tool to monitor expected and observed behavior, to detect anomalies, raise an alarm if significant residual references exist between executions. So we do offline pre-processing. I'm going to talk in a minute what this is all about, and an online verification and anomaly detection published in Usenet Security Conference. Okay, so you might think it's very straightforward, just like, you build a model and then an online tool and then raise an alarm, right? But no, because we are talking about the physical characteristics, right? It's not network traffic. It's sensor data, autonomous vehicles. AV's invariants are calculated using well-known nonlinear models. So control systems theorists develop these models. Accelerometer, gyroscope, magnetometer sensor data on the X, Y, and Z axis is used for the aerial vehicle. Vehicle positioning and steering angle is used for ground vehicle. You can see the complex model with all these parameters, right? K is state, input sensor, and then pre-processing sensor reading, commands to rotors, predicted states, and so on, right? Online stage, an extended Kalman filter. Kalman filter has been around for a long time. Control theorists use it all the time. So it's an extended Kalman filter, and it's used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. So the algorithm we have in 2 sections. One is prediction and corrects the estimation, and then we compare it against the sensor data. Anomaly detection, we use the CUSUM, C-U-S-U-M in the literature. We use that algorithm, is then used to detect the persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. Okay, so that's our design, and our implementation. We We didn't do it for sea because we don't have oceans. I guess we could have gone to our lakes, but we only did it for aerial and ground. For aerial autonomous vehicle, we used Intel ready-to-fly zones. You can see drones, controller PX4, flight controller, focused on detecting GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope after 1.5 seconds, and overhead is 5.43%. For ground, we use, you can see all the cars, we use custom built on top of Traxxas Ford Fiesta Rally Chassis, controller ROS Kineticam focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds, overhead introduced 2.25%. Each threshold produces probability of false alarms of about 2%. Okay, so this was our implementation. Now, we cannot forget about privacy, right? So for instance, we focused on attacks, but we may not want people to find out our location. Like, let's say I'm a smoker and I smoke in the car. We don't want people to find out that I'm smoking, okay? Because, okay, we know that smoking is bad, but again, it's what I'm doing inside my car. So we don't want people to take photographs and then send it to my insurance company and then my insurance getting denied, right? So beyond the security of individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles and motion sensors on lampposts and surveillance cameras to help identify traffic jams, reroute vehicles, and increase vehicle safety, right? So from the user's perspective, privacy concerns arise from all the information needed by such system that could lead to private information being exposed, such as vehicle identification and driving patterns. Legislators, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. So this will aid at improving the public perception, reduce hesitation from customers, and increase the adoption rate of new technologies. So without a doubt, privacy is critical, but we also need security, both. Okay, so now I finished part 2, which is security and privacy for Internet of Transportation systems. Now we come to part 3, that is, how do you apply part 1 and to part 2? Applications of security and AI for Internet of Transportation and infrastructures. So, data science AI for transportation security. Internet of Transportation systems are subject to attack like any cyber physical system. Streaming data is being collected from such systems, including autonomous and in the future, driverless vehicles. As transportation systems go electric, need energy conservation. So we know that, right? So we need in energy conservation. So it could attack the energy and tell us that, that we don't have, we could get stranded in the middle of the road in the highways, right? Because it can do some bad things which are with our energy. So data science, machine learning techniques could be applied to analyze the data. And the question is, can stream analytics, what we said, right? The ensemble-based model updates, the learning be applied to say financial, that we are applying for financial data, can be applied for telecom data, and telecom data can be applied for transportation data. That's a sensor data. So I had mentioned Kalman filter for certain types of security attacks, but we need to first identify all kinds of attacks, right? It's not just the attacks to the gyroscope. Remember, it could attack our whole energy in the transportation system, right? So there could be so many dangerous things happening. So how can machine learning be used? The main question is to understand the nature of the complex transportation data. It's not just like financial or network data, and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, so that's data science for transportation. What about adversarial machine learning? Because yes, we are applying machine learning for transportation systems, not just for security, but to coordinate all of the transportation systems, to check for roadworks and tell their driver the best route to take. And we want also to look at the communication between the trains and the trucks and the cars and give advice to the drivers. So lots and lots of advantages using machine learning. So Internet of Transportation will depend heavily on data science machine learning techniques for various applications. And this would include optimum directions, driving without a human in the loop, and so on. But remember, the adversary is watching, right? Adversary will be learning about our models used by the vehicles, as well as learn about the data used in the training of the models. Adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithm. So it's a game that's being played. So what sort of game? Is it zero sum? Is it Bayesian game? We have to understand Stackelberg game. We have to understand the data, and that's essential. And research is only beginning on adversarial machine learning for transportation systems. Okay, remember I talked about privacy, right? Privacy-aware quantified self, but now privacy-aware policy-based data management framework. So instead of a smartphone, we have replaced it with a car, and instead of healthcare data, social media data, we've got radar, GPS, cameras, LIDAR, ultrasonic sensors, and we have policy-aware data collection, storage, data analytics, and sharing, just like I mentioned earlier. Some of the data encrypted in the cloud, and we are using cloud-based services to query and so on. So my question is, can we apply those techniques to the Internet of Transportation for privacy-aware policy-based data management framework? This is the future. Okay, now another thing that people are talking about is trustworthy analytics. What's that? Computations of a big data may require massive computational resources, right? So automobile companies may use third-party service to outsource some computations. When a third-party server is used for computation, data inherently becomes available in untrusted environments, either observed by man-in-the-middle attack during data transmission or inside a threat from adversaries at the third-party location where computation is performed. In these cases, data owners may need to protect their data and require cryptographic guarantees about data security and integrity, okay, of computational output from these third parties. So how do you sort of secure the whole analytics, right? So trustworthy, formal verification of these analytics techniques. So one is looking at, of course, playing games with adversarial machine learning. Another is using formal verification and also do the analytics in hardware. So we are conducting research in secure encrypted stream data processing and trustworthy analytics using advancements in embedded hardware technology to support trusted execution environments. So we need to explore the applications to Internet of Transportation and infrastructures. Okay. So here is the SGX enabled platform, right? So we have users, you have secure connection, application library, SGX runtime, and all the encrypted code. And then you have the enclave memory where you are executing all the data analytics algorithms in a very trusted space. So you're ensuring that these machine learning algorithms will not be corrupted. Okay, so that's the whole challenge with this SGX environment. There are some articles that are not as positive, but we've had a lot of positive experiences, but we need to look at, do more investigation whether these SGX, these enclave memories could be attacked, okay? But still, this is showing a lot of promise. Okay, now my last chart, I think, I've talked for about, 42 minutes. So if there's time, then we can answer questions. But of course, if I'm giving it live, that's what I'm planning to do in about 9 hours from now. And then, of course, I'll be there to answer questions. Okay, this is just a backup, as I said. Developments in secure AI, integrating cybersecurity AI, data science is exploding. Applications of AI for security, insider threat detection, security for AI, adversarial machine learning, also developments in privacy-aware healthcare management, one's life activities. Yes, so security, AI and security for AI applications, AI for security applications like intrusion detection, security for AI would be adversarial machine learning, trusted analytics. And privacy, yes, there could be privacy violations, lots and lots of data being collected using machine learning. Privacy of the individuals could be violated. So we are proposing policy-aware, policy-based, privacy-aware data management lifecycle. At the same time, with the development of the Internet of Things, including Internet of Transportation System and infrastructures, security and privacy solutions are being developed, mainly physics-based solutions. As driverless cars become a reality, more and more of the AVs will use AI machine learning techniques. How can we develop AI solutions for detecting malware in autonomous vehicle systems? And how can adversarial machine learning work in such systems? And the main question, one of the big questions, can we develop a privacy-aware, policy-based data management framework for Internet of Transportation infrastructures, just like we talked about a policy-aware framework for our smartphones? Is it possible to perform trustworthy analytics efficiently when so much data is coming from all directions? Numerous opportunities for substantial research. And I thank all my colleagues. Okay, so I just want to leave you, oh, sorry about all these things. Okay. So I just want to leave you with some key points, because this conference is mathematics and computing. And so I focused on the computing part of it. But of course, there's so much mathematics, right? When we talk about control systems and control theories and so on, to model, it's like a physics-based solutions, to model these systems, right? We need to bring in mathematics for that, right? To model these systems. And then also for Internet of Transportation, model the autonomous vehicles. And then for game theory, that's also a lot of mathematics involved, for adversarial machine learning. And so this is very relevant. And if you read our papers that I've given you some of the listings of our papers throughout this presentation, and you would see that there's a lot of mathematics involved, in particular, like linear algebra and game theory, and also modeling physical systems like mathematical methods. And so this is very relevant for mathematics. And I'm now a computer scientist. My training actually was my undergraduate was in mathematics and physics, but now, for the last several, 40 years, I've been a computer scientist. So I'm more in the computing area. But I chose this presentation because it's very relevant for both mathematicians and for computer scientists. And also it's quite relevant for electrical engineers, control system folks, control engineers as well. So it sort of brings all of this together, and also artificial intelligence, right? So it integrates artificial intelligence, security, mathematics, physics, and control systems. So with that, I will end the presentation, and hopefully there won't be any technology glitches, and I will be there this evening, or tonight my time, 10:30, which is going to be about 10 o'clock your time, in India on March 3rd, 10 a.m. in the morning. And I will be there to hopefully answer questions, and there won't be any technology glitches. Okay, so I've talked, I believe, for about 40-45 minutes, and I was given about an hour, so we have about 10-15 minutes for questions. And again, thank you very much for listening to this presentation, and thank you very much to the organizers for inviting me to give this keynote address, and I'm really honored to have given this address. Thank you. Going to stop the recording.